All right. So let's see. Number 72. What do they tell us? Bicycle has wheels. Okay, that's groundbreaking. Oh, 28 inches in diameter. It's commoner. Let's say that one. Determines that the wheels are rotating 180 RPM. Okay. So I know the radius. What's the radius?
28 inches.
No. What's the radius? 14. All right, I love it.
Oh, there you go. Yeah,
All right.
there you go.
Radius is basically more important than diameter because it shows up in more equations.
Yeah,
Right?
you're right.
Sometimes. So the first thing I would do is collect everything I know for sure, right? That is a general life lesson. Just collect everything you know for sure. So what do we know for sure? We know the radius is 14 inches. We know that the rotation, what symbol do I use for that 180 RPM? What symbol does that get? Omega, because that's a angle per time, right? It's good old omega. Can we stop for a minute, you guys? Sure. Say again? What's 28? What's 28? What is 28? Diameter. And what's the radius compared to the diameter? Good, okay. All right, you guys all with me? So again, indicating the correct symbol for something is stupid important because that tells you which formula it's in, where to put it in that formula. So if you kind of like gloss over identifying what the variable is, you're not going to have a good time. How are we doing so far? I mean, this is the first step in a wordy problem, is just to identify what it is they tell you, right? Okay. What else did they tell me? Anything else? No. They asked me something. They want me to know, they want me to figure out the speed the bike is traveling down the road. What symbol would that be? What's another name for speed? Velocity. So what symbol do I give with the question? V. Okay. There. See, that's what I would do if I'm given a problem with a lot of words. I would identify all the information they give me and relate it to a variable. Because otherwise I can't use the equations, right? Now you look up equations for this. What is the most basic equation for this in terms of angular stuff? Okay, so velocity is distance divided by time, but there, I don't see any angular stuff.
Radius times omega.
Yeah. Which, right? Now what is omega? Is everybody with me? Why can't I just plug these numbers in? It's got to be in radians, right? Anytime you have an angle out in the real world, and now I've got enough, I can finally show, in a minute, I'm going to show you that shit. You ready? I'm going to write myself a note. Freaking angle inside versus outside. Okay. I've been saying this silly thing forever. We finally know enough we've finally gone over enough. I can finally show you what the hell I mean. Omega involves angles. Angle that's not inside of a trig function. It's got to be in radians to make physical sense. So now I need you to understand what I just did. And this is exactly what you do. Write down what you know, write down what they ask you, figure out the equation for what they ask you, step back and go, do I have everything I need? I do, except this is not in the, so now my immediate small problem is convert that to radians. How do I do that? Each rotation has how many radians? 2 pi. There you go. That's not bad, right? Take a minute, do it. Convert 180 rotations per minute, convert it to radians per minute. Go. I'll stand here and stare at you. Jeff is always doing his part. I have people I need to send rescue teams out for. Jacob? Hey. Christian, Hunt, Abdul, Allen, okay. I'm saying, I don't think come to class. All right. So this is how you do it, right? This is how you do. Anytime you have a unit you don't want, you want to replace it with a different unit, you can do this. And it's a very direct, I don't want rot. So how do I kill it? Put the rod on the bottom. And you told me how many radians per rod? How many rads per rod? 2 pi. Okay. Once I got that, what am I now able to do?
Multiply.
Put it in there, and then I'm done. Right? Does that make sense? I went too far, but I left something for you to do. Right? Yes.
So we have to multiply 180 times 2 pi and then put that answer into?
Yeah, so you're converting omega into radians per minute, which now this formula can accept. So whenever I do a problem like this, I was just talking to somebody earlier about don't generalize things too much. Don't look at this and go, let me memorize. No. What's important is, did you pay attention to why I did what I did? When we first look at this problem, I haven't done that problem in forever. I don't remember how to do that problem. So part of me is up here going, let me write shit down and hope to God I remember what to do. I mean, that's honest, right? I'm a human. I'm like, oh shit, let's hope this goes all right. But I desperately want you to notice the motivation. Why did I do what I did? That's what's important. Not, oh, when I see this kind of problem, I do this. No. I don't know if you're ever going to see exactly this kind of problem. Yeah?
Do we use the equation with v equals r times w or v equals d over c?
This would not be good because I don't know D or T. Right?
So we use the other one?
Totally.
Oh.
That's why this was a formula for velocity, but it's not good in this case because I don't know these. That's the better form because I know both of those. Does that make sense?
Yeah. Are we gonna have these formulas given to us on the test or?
No.
Oh.
Yeah, you gotta memorize them. I am pure evil incarnate, so you should know that by now. So you must memorize. How many formulas are there to memorize?
6.
1 million. No, it's not many. No, it's a little less than 1 million. It's more like 6. Yeah. Right. So, okay. Yes.
So how would they ask you, like, for linear velocity, like, what words would they use? Like, what words would they use to, like, for you to know that they're asking for a linear velocity?
Oh, speed. Traveling down the road. That equates to linear velocity. So so some of the problems might actually say linear. So that one says linear speed of a person who resides in the city, whatever. So this one is more just talking about it in real life. I'm not going to say, hey man, how fast are you going? My linear speed is currently, no, right? But that's what that means. Yeah, but that's a good question. Not going to use the exact words. Some of the problems are going to say just like you would say it in real life. And we have to understand that this is not me rotating. I am going forward. My tires are rotating. So this is very interesting. The tires have an angular velocity, which translates into me having a linear velocity, correct? Yeah. Yes.
I also have a quick question. So like on a word problem on a test, you would know the difference because like in real life, a wheel wouldn't be like going like this, it would be going like this.
Okay, sure.
Is that how you would determine it?
Sort of. Again, so let me see if I can get this. Slightly different problem. Let's say I have we're looking down on a record, right? And there's a bug. They love the problem with a bug on a record, a certain distance from the center. Yes? So if I turn the record on, the bug has an angular velocity, correct? He's also got a linear velocity.
From the center.
So here's the thing. Let me see if I can do this. Is this long enough? Maybe. No. He's doing some weird shit. Okay, so there. So I'm rotating this, right? So pretend like there's something stuck on the end. You with me? I stick it on the end, and then I'm rotating it, yes? So isn't it, it's angular velocity, correct? If it comes off, won't it fly off straight? So at every instant, it's got an angular velocity, but at every instant, it's also got a linear velocity. So right there, it's got a linear velocity. It just happens that a second later, now it's pointed that way. So if it just came loose, it would fly off in that direction. That is the real relationship directly to a bug on a record is experiencing an angular velocity, but it's also got a linear velocity. That linear velocity just happens to be pointing in different directions as it turns. So we're on the Earth, right? And the Earth rotates at not that speed, thankfully, at the same speed as the hour hand on a clock. Not this one, thankfully. We don't go. This clock is having some issues. But we are so far away from the center that our linear velocity is something like 1,000 miles an hour. Do we feel 1,000 mile an hour motion right now? Of course we don't. But we are going, if suddenly we flew off the Earth, we would go flying up into space at 1,000 miles an hour. If the Earth just suddenly went, stop, we would go, wah! So let's hope that doesn't happen, right? But we don't feel that because we are really going like this. We're just so far away from the center that the linear velocity would be 1,000 miles an hour if it came flying off. Okay, maybe. Is that better? Or worse? I don't know if that's worse or better. So you have angular velocity. The linear velocity is sort of hidden. It's what would happen if it suddenly came loose. It would fly straight off, correct? Can you guys, if I'm watching someone, when I throw it, like I let go of it, it's not going to go wee. It's going to go straight. Does that make any sense? No? Okay. I mean, what happens if you're on not a merry-go-round, but remember on the playground, those little things. Man, we did so many things on the stupid little things that we got so sick on this. I don't know. You guys know what I'm talking about? The little, what do you call them? I can't remember. Not a merry-go-round, but spinner, sure. That sounds good. I don't know if you ever did the thing where we would sometimes, of course we would try to make it go as fast as possible, but then somebody would try to make it stop suddenly. They would get themselves hurt, which is great. And they would almost have their arms, but everybody on it would basically be thrown in a straight line. We would go around the circle and then we'd go, ah! We'd fly off in a straight line. Of course we would. Anyway, okay, enough. I'm not gonna. Okay. Anything else I can expand on? Yes.
Completely different problem, but 45 on 7.2.
What is it? Sorry. 7.2. Which one am I in now? 7.1. Okay. 45. You said.
Yeah.
All right. Oh yeah, this is one of my favorite. I just want a student to go. There it is. All right. Can you see? At the moment, what are the only triangles that trig functions work with? Right triangles. How many right triangles do you see up there? I see 2. One of them is right here. Right? So let me see, for the people at home. People at home. Da-ba-dee-da-day. 45. Do you guys see that? It's not as skinny, but poor little dude. But I put him up on the board, right? Is everybody cool with that? I just drew the tinier triangle up here, correct? Can you find this? I basically already have the work up there, but what trig function relates to those sides? Tangent. So tangent of 70 equals y over x. Bam. Right? Then you figure out what that piece is, correct? What about the big ass right triangle? You can find its complete side here, right? So what would you do with this and this to figure out that?
Add it.
Subtract.
Subtract. This is too much, correct? This is more than the answer. Do you agree? How much more? This much. Well, if you find what I called A, and you find this, you subtract them to get what's left. You can see that. Well, let's do this, okay? Figure out what A is. Figure out what A is. Don't say it, just figure it out. And then draw the bigger triangle by itself. If you need a calculator, I have some, I think. Yes. You're going to need a calculator here in a bit. We're going to have a worksheet. I'm like, huh? You're sure? Earth, fire. All right, here, appreciate it. Sure. So if you solve this, you should get 119 over tangent 70, and you can do that in your calculators, right? Just be careful. What do you want to check before you plug that in?
Whether it's radians or degrees.
Whether it's radians or degrees.
When you're doing a problem like this, your calculator should be degrees, right?
When you're doing a problem that has degrees, your calculator should be degrees. Well, that's neat. Don't freak out. That's calculus. We're not going to do that. Somebody froze an image and it's still there from yesterday. I'm going to unfreeze it. Bye, little image. Okay. Freaked me out. I'm like, it can't be me. That's way too nice writing. So if I hit mode, right up there, mode, I can tell if it's radians or degrees. So it's in degrees, which is good. Why is it good? It's in degrees because the angle's in degrees. That's all. So what do I get for A? Have you guys tried that yet?
43.3.
All right, let me catch up. Okay, 43.31, we'll say. Have you drawn the big ass triangle?
Yes.
What's here? 26. This is 119, and now let me call this B, just because. Can you figure out what B is? And again, every damn time I do a problem like this is not like, here is a class of problem. You could do that, but that's insane. You have to sit there and go, especially right now, where are my right triangles? Let me look at those and see how they relate to what they want me to find. So the big ass right triangle is this whole thing. The little one is this thing. And then it's a physical reality. I subtract those to get what they want from me, right? It's a very physical idea. How do I solve for B? What trig function do I use?
Tangent.
Holy shit. Yeah, all these are tangents. Oh, 119 over B, right? So B is 119 over tangent 26, which is about
243.98.
243.98. That's a lot. And then just to kind of draw in now, different color would be nice, Jeff. Here is this triangle, correct? What was this? This was A, right? Right? So how do I get what they want me to get, which is this piece? Well, I do B minus A. You guys see that? You guys see that? That's a very physical idea, right? Just chop A off of B and you're left with what they want. Is that all right? Okay. Yeah, it's not okay, Jeff, but I understand it. All right. That's fine. Anything else from homework stuff? Okay, okay.
How do you rewrite the equation as b equals 190?
Oh, I can multiply by b and divide by tangent. Right? So, very quickly, I can't remember if I showed you guys this. You ready? This is ground shaking. What's 10 divided by 5? 2. What's 10 divided by 2? 5. See how these can just switch places and it's still true? Of course it is. 10 divided by one piece is the other piece. So I have this divided by b is that, so then therefore this divided by that is b. They could just switch places the same way the 5 and the 2 did. That's a beautiful thing to remember. What's the long cut? Multiply by b, divide by tangent, and of course you get there, right? Let's start using some shortcuts. Yeah. Let's see. Oh, it's right here. This guy? Oh, this guy. So the one about the monument?
Yeah.
Okay. Were you here? Yeah, you were here. We drew the picture, right? So now, no?
It's on your YouTube.
It totally is. So I didn't want to do more until, did you see that when we drew the picture yesterday? Okay. See me after or watch the video.
Okay.
I want more people to try that based off of the hint I gave yesterday. And if you try it and you still can't get it, then ask me.
I tried it and I still can't.
Well, there you go. Okay. That's what I wanted. All right. So just to get back to where we were, building, person in a window, monument, angle of elevation was, what was it, 15? Yeah. Angle of depression was 2 degrees. This is obviously drawn very much to scale. What's probably is this was further away, then the angles would make more sense. But I'm just drawing an angle picture. Doesn't have to be perfect. And I know that this is, what was it, 200
Yes.
somethings feet? And they want to know what this distance is here, right?
Yep.
Do I see right triangles?
Yes.
Yeah, I see 2 of them. I see this one and I see that one. So, again, one thing you can do is draw each of the right triangles you see by themselves. X, 15 degrees. I'm going to turn, well, it doesn't matter, Jeff. It really doesn't matter. 2 degrees. It looks like 20. 2 degrees, X. Right? Now, what's interesting is how long is this? I don't know. Right? So what do you want to call it?
Y,
No way. And then what must the other one be?
200 minus 1.
200 minus y. All right, let me stop for a minute. So a huge part of these wordy problems, a lot of them is going to depend on can you draw the picture correctly. If you don't draw the picture correctly, you're never going to get the answer, right? And then the second thing is, can you find your right triangles? If you can, just draw them by themselves so there's less crap around them. You can just focus on them, right? Okay, I'm going to take this picture away. What can you write from the first problem? From the first triangle, sorry.
10, 15,
Second problem, second triangle.
10, 2 degrees, 2
Good. Which variable do you not care about?
Y.
Aw, a little what? So if I solve this for y, can you solve this first one for y?
Why is the second triangle tangent
What would it be? So the triangle's upside down. I could draw it. I could just flip it. So this is x. This is 20. Yeah. 2, and this is 200 minus y. Same triangle, right?
Oh.
That's all. So in the base. All I care about is my angles in the base. I don't care if it's flipped up or flipped down. Okay. Can you solve this for y? Why am I solving for y?
So you can plug it into
Yeah,
Y and
because
then
again,
equation.
I don't care what y is. I care about what x is. So let me solve one of these for y, because then I can replace y with this. And then I have an equation that only has x's in it. So I think I got to this point with you guys.
Yeah?
So all right, don't say that, John. It shouldn't be that terrible from here. It really shouldn't be. So if I take, I'm going to take these away. If I take tangent 2 degrees equals 200 minus
X,
x tangent 15 over
X.
x.
200 minus 1.
Totally, what's y? What's y equal?
X 10, 15?
Totally. So wherever I see a y, I can replace it with what it is.
Uh,
Oh, okay. Now I have an equation with only one variable in it, correct? Okay, cool. What is it about this problem that makes it look worse? What do I wish wasn't here? The denominator. So how can I kill it? Yeah, so many equations. If you say to yourself, man, why is this equation gross? Let me kill that, right? Now this is not a life lesson, this is a math lesson, right? You don't do that like, don't go, I don't like them to kill it. No. Don't want a lot of little Dexters running around. So if I multiply both sides by x, let go of the fact that there's a tangent 2 and a tangent 15. What are those? What's tangent 2 degrees? Don't tell me the answer, just tell me, what does it represent? Like, what is the square root of 11? It's a number. What's tangent of 2 degrees? A number. What's tangent of 15? A number. Do we let numbers scare us? No. They don't mean, yeah, we created you numbers, right? So that, I think, is what gets people down. How do you solve this for x? How do you solve any damn equation for x? What do you try to do first? You try to get on one side, you try to get all your... How do you solve any equation for x?
everything that isn't X.
Everything that's not x on one side, everything that is x on the other side, yes.
I'm confused how if you multiply it by x, wouldn't it be 200x?
No, because what happens right here,
It cancels.
okay, which is why we multiply by x in the first place. Yeah, don't make this quadratic or something. No. You don't want a quadratic trig problem yet. What's in the wrong place? Let me ask you like that. What's in the wrong place in this equation? No, what specifically? What term is in the wrong place?
200.
10.
What's on this side? I have one term, correct? Does it have an x in it?
Yeah.
Yes.
Do I have all the stuff with x in it on one side?
No, you don't.
Which thing is in the wrong place?
X 10, 15.
Thank you. So how do I get that on the other side?
Added.
Add
Add
it.
it to both sides.
Yeah.
So then would it end up being tangent 17?
Okay. Okay.
Oh,
Okay. Square root of 5 plus square root of 2, is that square root of 7?
No.
Shit, no. Hell no, right? Hell no. What are now, I know we're not talking about radicals right now, but I want to go back to a function we worked with before. Aren't radicals exponents? Yes, it would be 1/2 power. Can I add before I do the exponents? No, let's do a problem we know. Square root of 4 plus square root of 9. What is square root of 4? What's square root of 9? That should be 5 then. So if you think it's the square root of 13, you are obviously wrong, correct? I cannot add the insides of two functions together, right? Is that all right?
So then if you add that to the other side.
You're just going to get, unfortunately,
Okay.
this. But we don't care. Let me ask my standard question. How many x's do you see up there? Nope, I see 1. Haha. I see 1 x that was distributed. So let me undistribute the poor little dude. Do you see what I'm saying? So always, when you don't have like terms, but you have a lot of stuff that have the variable, you get them all on one side and you take it out. Then there's just one of them, right? Yes, we've done that before. Just because I got tangents now, I don't care. We do the same exact thing. Take an x out. So now I've ended up doing the whole damn thing, damn it. And then divide by the shit you don't want. Yes? Anytime you have the variable trying to solve for in multiple places, get them all on one side. Everything that has that variable in it on one side, and take the variable out. Okay, and then you just throw that in the old calculator. See what it says. Old calculator. I'm gonna guess. I don't know. I don't know. My guess would be it's pretty big. My guess would be it's pretty big. What would that be, Jeff? I don't know. I don't have a good guess. 800 feet, 1,000 feet, maybe a few miles. I don't know. 5,000 feet. Anyway, all right. I guess I won't find it. Okay.
I'm getting a negative number.
You are in degrees. Hit the mode.
Yeah.
Okay. Interesting. So it would be 200 divided by tangent 2 degrees plus tangent 15 degrees, right?
Oops, sorry, I subtracted.
Ah, okay. Okay. Can you guys understand that you cannot say, oh, the monument problem, this is how I do it? There's none of that shit, right? Which on one level is bad, I understand, because you're all like, I want that. I know students want this kind of problem, I always do like this. But it's also good. You don't have to memorize as much. You take the situation you're given, you draw it, you find your right triangles, and you work with them. There's nothing beyond the basic trig stuff to memorize. You don't have to memorize this kind of problem, I must memorize the steps, and this kind of problem, I must memorize. Shit, no. Yes?
How'd you get rid of the x to do 200?
I don't know. Oh, right here. Are you cool with this step?
Yeah.
Then I just divide by that.
Then where'd the x go?
It's. I'm sorry. It's still here. I just didn't write that. I just was
Oh,
focusing on what was being plugged in the calculator. Yeah. Okay. All right. So, it's enough questions. So if you have more questions, see me after class. Let's do a quick review of everything we know so far. By the way, what'd you get, Megan, for that?
660.
Cool. All right. Sorry, I just want to know if it was close to what I thought it was. So we know, given a triangle, we know sine, cosine, tangent, what else? Cosecant, secant, cot, I love it. So you can make all those, you need to memorize all of those ratios, right? So what I'm hoping helps, and this helps you remember the ratio, it helps you work with a triangle. Sine likes y, cosine likes x, tangent likes Sine and cosine. And then these guys, once you know those, you know those. So really, if you just know sine and cosine, everything else can be built. You with me? So you don't have to memorize 6 things, you memorize 2. So I've cut it down in third, by 1/3, right? So this is just the reverse of sine, this is just the reverse of, you could do it, Jeff. Reverse of cosine, this is just the reverse of tangent, okay. Okay, I like it. We also know now, can somebody tell me what sine of 0 degrees is?
1.
I have extreme opposite answers. Hello. What is sine like? Y. At 0 degrees, do I have any y?
No.
It's all x. Sine hates it there.
Okay.
Right?
So the cosine is.
What's sine of 30 degrees? So think about him like a little turtle. Sine does not like it on the x-axis, totally in his shell. Go away from the x-axis just a little bit. He's like, oh. So what's the next number up? 1/2. So you know it could be 0, 1/2, rad 2 over 2, rad 3 over 2, or 1. Those are the main things for the angles we're supposed to memorize. So sine of 30 is going to be still a small dude, more than 0, because at least it's got a little bit of a... So again, on the unit circle, if I'm at 0, there's no y piece. If I go to 30 degrees, do you all agree there's now a y piece? Is not as big as it will be here, here, or here, so it's got to be the smallest option. So when I get to 45, it comes out a little more.
Root 2 over 2.
Root 2 over 2, because this is root 1 over 2, and this is root 0 over 2, right? So what's going to be at 60 now? Now it's really getting more bold. And then what's in the 90? 1. Now it's fully out. Because he loves it on the y-axis, right? Turtle's all the way down. Cosine does all this shit in reverse, right? Because cosine is the turtle that loves the x-axis, and then he brings his head in as he gets further away from the x-axis. And again, on these triangles, these beautiful triangles I've drawn, you can see the y growing. You can see the x for each triangle shrinking, right? At this triangle it's fairly tiny. At this one it's bigger. And then when you get to here, there is no x piece. So another way to look at, one way I kind of like looking at this is cosine is the shadow that you would get if you had a flashlight shining from up here. So if I had a triangle here, the shadow would be there, yes? So if I have something sticking straight up and the flashlight, there's no shadow. You guys understand? There have been pictures posted of the sun is directly overhead and there's this post and there's 0 shadow because it would be directly under itself. Yes? Okay, maybe, okay. So there's a lot of different kind of ways, and once we learn a little bit more, I'm going to start showing you some cool animations to kind of explain. So once we start graphing these things, right? I'm going to show some cool animations to show you how they get put together. Okay, so I'm going to give you this little worksheet. I really, really want you to work together. I'm tempted to, I think I will. I haven't done this in a while. I'm going to put you into groups, just because. So if you don't like that, too damn bad. Okay. Such a caring teacher. By the way, I keep forgetting to mention this, but if you haven't logged into Canvas, you should, because they're asking you to do evaluations on me. Right? So if you really just hate the shit out of me, just get in there and tear me up. I love constructive criticism, so if there's something I could be doing better, let me know. So make sure to log in so you get that prompt. Sure. All right, guys, let me see. Okay, I'm not going to make you move too far. So you three back there, doing one together. You with me? And then you three right here. You guys with me? Yes, yes. And then you three right here. Yes? Okay. So like you're gonna have to like turn around and 3 right here, back here? Yes? Let me see. This is where it gets interesting. So those 3, you 3, and then you 3 here. Those, yeah, okay, good. And then you guys, you 3 here, cool. And then like group up. This almost works out perfectly. You 2, and you 3. Go for it. Turn around, look at each other, help each other out. All right, guys, I know you're not done. I'm just going to kind of catch up to you a little bit. Okay. Part of why I like to give this kind of worksheet, and again, like I said, you're all still uncertain about a lot of this stuff. This is the perfect time to make a bunch of mistakes. Just get it all out your system. It also helps you see why a mistake is a mistake when we kind of go over it together. And I also don't want to show you all the ways I do it because I want you to kind of develop your own way, but I'm going to show you the way I would do number 1. The fact that it's in the 4th quadrant, that only tells me one thing. It tells me what the signs are going to be. By the way, now I have to do this. S-I-G-N, signs, yes? Because now we have signs. Okay. Why does this make sense that it's negative? Because in the 4th quadrant, y is negative, so of course sign's negative, 11. I kind of let go of that at first. I can just throw the SIGN, the signs in at the end, right? I could put the positives and negatives at the end. Can you draw a triangle that would relate to sine theta equals 6 over 7? What would be 6? Which side? Sorry? So the side across from theta, I would accept that, right? That's 6, and where's 7? Okay, there you go. This is the part you should all be jumping on. Now, immediately, sorry. What I'm trying to say is that it is so much easier if you don't throw the negatives into the middle of your work. At the end, let me ask you this. In the 4th quadrant, is cosine negative or positive? Positive. So whatever numbers I get, I'm going to leave it positive. Do you guys understand? This is the way I would do it. Could you draw a triangle and put a negative on the 6? Of course you could. But that could lead to some mathematical mistakes. So personally, I put the signs on at the end. Because that's all. The fact that it's in the 4th quadrant, the only thing that tells me is what the sign is, a negative or positive, correct? The numbers I have memorized. They're always the same. You guys with me? You don't have to do it this way. If you like the way you did it, when you had a negative in there, keep doing it. But that's a great place to make math mistakes. So what's this last side going to be? Do you guys do that? Square root of 13. So if you didn't figure out the last side, I don't know how you set up the ratio. So you need all the 3 sides, yes? How to get 13? 49 minus 36, right? Square root. So no, sine theta is negative 6 over 7. What do we automatically know? If I know sine theta is negative 6 over 7, what's the one that's the easiest thing to immediately get? Cosecant theta is what?
Negative 7 over 6.
Holy shit. Okay. From the triangle, what's cosine?
Root 13 over 7.
Root 13 over 7. Now, is it positive or negative? Positive, because I'm in the 4th quadrant. See, that's where the plus and minus comes in. The quadrant I'm in, all it does is tell me whether something's negative or positive. So I put that shit in the middle of my work if I don't need to. Now, if you want to, it'll work if you do it correctly. It just opens up more and more places to make mistakes. So what's secant?
7 over root 13.
Which becomes multiply by rad 13. You always have to rationalize. All right, so what's tangent? Tangent theta. Negative 6 over rad 13, right? I like it. Y over x. which will be negative 6 rad 13 over 13.
How did we get rad 13?
Square root of, so 7 squared minus 6 squared. Right? So it'll be, if I call this x, x squared plus 6 squared is 7 squared. 49 minus 36 is 13, square root 13. Okay. So what's cotangent? I go back to the original form this was in because now what's cotangent? Negative rad 13 over 6. Yeah, just got to flip that dude, right? Flip that dude. Become a 3. You guys okay? If you didn't quite get all those, do you see how that works? And again, this is a suggestion. If you like making the 6 negative, do it. I don't. Right? Because it's an easy place to make mistakes. Okay. All right. And an early favorite problem was this one, these ones. I need you to start forcing yourself to work with radians directly, right? So for example, 2 pi is also 8 pi over 4, right? Correct? 2 pi is also 12 pi over 6, right? So 11 pi over 6, did it get all the way to 2 pi? If 2 pi is 12 pi over 6, did 11 pi over 6 make it? How short did it come? 1 pi over 6. So as you think about the angle I'm given, how much did it go? Did it go short or did it go past? That's the reference angle, the amount that it came up short or the amount that it went past. Does that make any sense? Okay. So for example, if I had to do, doesn't matter, Jeff, secant of, what you got? What are we doing here? Okay, yeah. Secant of 15 pi over 4, right? 15 pi over 4. What number is 15 close to that would work really well with 4? 16. So 16 pi over 4 would be 4 pi. So if I went 15 pi over 4, it's just short of 4 pi, correct? 1 pi, 2 pi, 3 pi, 4 pi. It's just short by how much? By how much? 15 pi over 4 is just short of 16 pi over 4 by 1/4 of a pi. Pi over 4. That's my reference angle. That's how short I came. Reference angle is always in reference to, that's why we call it reference angle, in reference to x-axis. So what if I had, doesn't matter, Jeff, tangent of, it still doesn't matter, Jeff, 13 pi over 6. Let's make it negative. Yeah, negative 13 pi over 6. What's 13 close to that works well with 6? 12. And what's 12 pi over 6? 2 pi. So negative 12 pi over 6 would be 2 pi. So if I go negative pi, negative 2 pi, did I stop short or go past 12 pi over 6? Right? That's more than 12 pi. Yeah? So I went past how much? 1/6. That's pi over 6. Reference angle. Done. Dunzo. And again, this is new. We just learned radians like a hot minute ago or so, right? Relative to the universe. Okay. So 11 pi over 6, stop short at 12 pi over 6, which would have been 2 pi. So I know I'm in the fourth quadrant. I know my reference angle is 11 pi over 6. So this equals, is sign negative or positive here?
Positive. Negative.
Because the y is down, right? So it's negative sine of pi over 6. And sine of pi over 6 you have to have memorized. Or do like here's what I'm thinking right now as I'm looking at you. I'm thinking sine likes y, pi over 6 is close to the x-axis, sine's going to be small, 1/2. Pi over 6, closer to the x-axis. Sine don't like it there, it's going to be tiny, 1/2. And again, if you don't like that way of looking at it, you can memorize it a different way. It's just the way I like. You don't have to do it that way, right? So what about negative 480? Now it's degrees. This is a little bit better. So if I go back 360, how much more do I go?
You have to go into the third quarter.
True, because how much more do I go? 120. This would be 90, so I go, how much short from 180 did I get? 60 degrees, exactly. So my reference angle is 60. Is cosine positive or negative here? Negative, so this is equal to negative cosine of 60 degrees. Is that all right? The reference angle tells you what the number's going to be because you have those memorized. The quadrant tells you what the sign's going to be, just like this one did. What's cosine of 60? Cosine likes x. 60 is far away from x.
It's minus a half.
Minus a half. Okay.
Yeah.
So again, if you really don't like the way I look at it, I am completely fine with that. You need to memorize these. You must memorize cosine and sine for all the angles, the important angles in the first quadrant. Because the other quadrants, they repeat the numbers. It's just positive or negative. Yes?
How do you know that sine and cosine are
In the fourth quadrant for this problem, isn't that below the x-axis? Wouldn't the y's be negative down there? How would you label this scale here? If you wanted to label this? Negative. Y's are negative. Sine goes like y, sine's negative. This axis, this quadrant, cosine, this x-axis is negative, correct? Cosine of x, cosine's negative there then. That's straightforward. Again, SOHCAHTOA, one more example of how it sucks. Sucks big rocks. I'm sorry. A lot of my colleagues teach SOHCAHTOA a lot, so I'm not trying to say anything bad about them, but SOHCAHTOA only helps out this much. If you know cosine likes x, sine likes y, so much shit suddenly makes sense, is my hope. Okay. And you can always double check these in your calculator if I'm letting you. Now, this is a good example of where I'm definitely going to have a part 1 and a part 2 on a test. Do you guys understand? Part 1, no calculator, bunch of this shit, right? Part 2, this shit, because you're going to need calculators for this. This is your old classic Hobbit's Mount Doom problem. This is classic. No, it's not. Okay. What about this guy? What is 13 close to that 4 would work well with? 12. 12 pi over 4 is? 12 divided by 4 is? 3. So if I go back 1, 2, 3 pi, I go a little more than that, correct? How much more than that? Say again? A fourth, yeah, pi over 4. So my reference angle is pi over 4. 12 pi over 4 would be perfectly 3 pi, right? I went the wrong way. And then 13 pi over 4 is 1/4 of a pi more. That's my reference angle. That's how much I overshot the x-axis. Cosecant is related to sine, so this would be 1 over, is sine positive or negative here? Positive. So I'm not going to put a negative there. Sine of the reference angle. So cosecant is 1 over sine. This has a reference angle of pi over 4, and I left it positive because sine is positive there. Do you see how all that comes together? And again, this is 1 over. I don't give a shit because I know what sine of pi over 4 is, and then I can just do 1 over that because I've memorized sine of pi over 4, which you definitely have. What's sine of pi over 4? No. I want to be really careful, really careful. When I say what's sine of pi over 4, the answer cannot be an angle. Inputs of trig functions are angles. Outputs are numbers representing ratios of sides. So I'm not asking you to convert pi over 4 to degrees. I'm asking you, what is the sine of pi over 4? Rad 2 over 2. And then I just have to do flip it. So if you flip it, you get 2 over rad 2, and if you rationalize it, these cancel, you get rad 2 finally. Blah, blah, blah. Okay. Oh, shit and a half. Time just goes. Real quick, this guy. Can you guys see that this is a stop short? Do you see how it stopped short? How much did it stop short? 30 degrees, that's the reference angle, right? It didn't shoot past, it stopped short. So I could do this. Tangent is sine over cosine, right? Of the reference angle. But what is negative in this quadrant? Sine. And what's in cosine, of course, is positive, correct? So negative sine of 30 over cosine 30. That is the same thing as tangent of 330. Is that all right? Because tangent sine over cosine. Reference angle is 30. Sine is negative down there. So what's sine of 30 degrees? Good. Because sine likes y, 30 is close to the x, sine doesn't like it there. What's cosine of 30? Cosine loves it there. It's close to the x-axis. Root 3 over 2. Pi over 4 is an angle. The over 2's cancel. And then you rationalize and you get negative rad 3 over 3. All right, I'm just going quick a little bit because we're out of time basically. But so we'll finish this up next time. We're going to get into graphing. So now we've learned 6 new functions, correct? So obviously, what do we like to do with functions, especially in pre-calculus? We like to graph the shit out of them. So we're going to graph them. We're going to move them around. We're going to press them. We're going to stretch them. We're going to do all that stuff. Yay! Okay. All right, guys. Sorry. I'll see y'all tomorrow. Oh. Quiz. Let me just keep it rolling. Let me just. Thursday. Yeah, that's exciting, Jeff. 6.6, 7.1, 7.2. Oh my God, Jeff. They're evaluating you, man. I know. They can tear me up. There you go.